For our listeners, I think a lot of people have had the chance to read the credit card debt and read the test score papers. The under specification paper, we read it and it was great. I would love to know in your words, maybe how you would, what the lesson you took away from the experience of writing that paper is, and what
the under specification paper.
Yeah, the under specification papers. Like, how has it impacted your thinking about engineering ML systems now?
Yeah, so for folks who haven't read that paper, for me the key takeaway was, let's see. So for a long time, people have worried about especially back in the dark ages when we went from sort of models that were trained with convex loss functions to all bets are off, deep learning, non-convex, blah blah blah. There was a lot of worry about like, well, wait a minute, are the results going to be reproducible? Things like that. And empirically, what's happened is that folks have found, by and large, the results on IID test train splits for deep learning models tend to be really pretty repeatable. I mean, not exactly, not byte for byte, not to 6 decimal places for each prediction, but really pretty repeatable. And what this paper looked at was what happens when you do an evaluation of repeatability in training deep networks, and you look not at an IID test train split, but you look at one of these stress tests that's explicitly from a slightly different distribution. And there what we found was that actually a lot of that repeatability went away when we look at out of distribution performance. And so this was just with like the minimal possible changes that you could have from model training to model training. It was just varying the random seed that was used to start the models. Everything else remained constant. And we saw pretty large variation amongst different versions of a model where each version was trained with a different random seed on things like perturbed versions of ImageNet or interesting genomics use cases or stuff like that. And the range of that variation was often larger than the range of variation between, say, a good model and a not so good model in like some ML competition on that task. So qualitatively quite large. For me, this is A, really interesting, and B, a little bit worrying, because if a given random seed changes your performance on out of distribution data, and we believe that out of distribution data is something that we encounter every single day in the real world.
That's exactly what we encounter, right? Like it's so messy.
Yeah, then we maybe do have some issues on repeatability there. So I think that there are some reasonable solutions. Like in one of our other recent papers, we found that model ensembles, like just taking n copies of the same model, but maybe just with different random seeds and ensembling them together, gives a lot of robustness in these domain shift settings. Like obviously there's some additional cost to be paid in terms of both inference time and in terms of system complexity, but there does seem to be some really nice robustness benefits that are consistent across domains and across application areas. So that's one takeaway, but my main takeaway from this is just that, wow, it really is important to be evaluating models on these out-of-domain stress tests and to make sure that we understand the implications of what we're thinking about when we're in deployment land.